Hey everybody, welcome to the second installment of Unit 2. So far we've talked about chemicals and how to classify chemicals based on their physical and chemical properties. And we also talked about the physical and chemical changes that can occur with different chemicals. However, we really don't call everything chemicals, but instead in chemistry, we say that we study matter. So what is matter? And this is probably all of you wondering what matter is, especially wondering what that monstrosity of a computer is that he's looking at. But matter is anything that takes up space. So all of you are made up of matter. The air that's between you and your iPad or your computer right now is made up of matter. It's taking up space. This little crystal that I have right here is made up of matter. And the only reason I have this here is because I just filmed another video for my AP students. Almost everything you can think of takes up space. It's made up of matter. And that's what chemists study, is they study matter, the processes that matter undergoes, and the energy changes, and we talked about that before. We can categorize matter in a few different categories, which is what we're going to do in today's lesson. So there's really two broad categories we can classify matter in, but we can break down those categories a little bit farther. And the first category is a pure substance. So if something is pure, you think, well, it's just that one thing, it's pure. And that's what a pure substance is. And there's three different types of pure substances. There's atoms, there's molecules, and there's compounds. Three different types of pure substances. Most things, however, are not pure. They're made up of a multitude of things. And in those examples, they are called mixtures, which really is what most matter is. It's some sort of a mixture. And mixtures can be one of two types. They can be either homogeneous mixtures or heterogeneous mixtures. Let's go ahead and talk about the difference between all of those. Pure substances, like we said, a pure substance is any single type of material. It has to be just one thing. So any single type of material that has not been contaminated by another substance. So I really don't have any pure substances around me because it's very difficult to find a pure substance of something. It's not been contaminated. A good example would be table salt. Let me actually grab the salt. So salt is an awesome example of a pure substance. Every little thing in here is made up of the same material, sodium chloride. That's it. This is a pure substance. And this is one type of pure substance, but that's actually not the first one we're going to talk about. We're going to talk about atoms or elements first. So one type of pure substance is an atom, and that's when you have the smallest unit of an element that maintains the properties of that element. So it's as small as you can get, but it has the properties of that element. I actually have a pure substance atom or element in this case. If it's an atom, it has to be just one element because they're all the same. So, and I have bismuth, which is number 83, I think, on the periodic table. So this right here is a bismuth crystal that I bought. And in this sample, every single atom is a bismuth atom. So in this one structure, this is made up of one type of atom. That's it. So, oh God, it's cracking. I have to be very careful with this. So this is the smallest unit of an element that I can get. So this would be an example of a pure substance element, which is made up of atoms. One type of element on the periodic table. This is bismuth, and this is how it grows naturally. It forms this really cool structure, and it forms this really beautiful, like, iridescent color. So I love this. When I saw this in real life, I knew I had to have it. So there's my pure substance atom or element. And then there's molecules. Now, molecules can sometimes be broken down into a much more simple and stable substance. And your molecules are formed when you have two or more atoms that are joined together chemically. Molecules have to be two atoms bonded. That's it. two atoms that are joined together by a bond. And these can sometimes be broken down into something more simple and more stable. So here's an example of a molecule. I have hydrogen just bonded to itself. Hydrogen doesn't like to exist as just individual atoms, so they'll always have a bond between them. But I have one atom of hydrogen bonded to another atom of hydrogen. They're joined together chemically, therefore that is a molecule. We also have compounds though, and compounds are very similar to molecules, but there is a very minute difference between them. Compounds are formed when you have two or more different atoms that are bonded together. So, for example, salt. Salt is a compound because I have sodium bonded to chlorine. And in that case, they are different atoms that are bonded to one another. Therefore, this is a compound. And you can break compounds down into more simple and more stable substances. So because salt is made up of sodium chloride, NaCl, you can break salt up into its constituent elements. You can break this up into sodium, and you can break it up into chlorine. You could separate those two. Let's go ahead and differentiate just between molecules and compounds here. So this right here, water. Water is a compound, of course, because this is two or more different atoms are joined together. I have hydrogen bonding to oxygen, two or more different atoms that are bonding to make this molecule. This is a compound. Is this a molecule? Well, yeah, molecules have to have any two atoms that are joined together. So in this case, water is a compound, and it's also a molecule. Let's take a look at hydrogen here. We've already established that this is a molecule because it's two atoms that are bonded. However, is this a compound? The answer is no, and that's because compounds have to have different atoms that are bonded. If I have hydrogen bonded to another hydrogen, it's the same thing. So therefore, that's a molecule, but it's not a compound. It's kind of like in math class where you talked about like all squares are rectangles, but not all rectangles are squares. In this case, all compounds are molecules, but not all molecules are compounds. Molecules have to be just any atoms bonded, whereas compounds have to be two different ones that are bonded. Let's go ahead and do sample problem 1 together. So what we're going to do is actually categorize all of these different things that are listed up here, either as atoms, as molecules, or as compounds. But before we do that, let's actually very briefly describe each of them in very simple terms, and then say, can we break each of these down? So if I were to describe an atom, just in very simple words, I would describe an atom just as the smallest unit of matter. Literally, we cannot get anything smaller than an atom. If we do, we just have subatomic particles, but they don't have the properties that love have. Can we break down elements? Or can we break down atoms? And the answer to that is no. Absolutely not. If I break down an atom, I'm not going to have that atom anymore. It's not going to retain its properties. So no, I cannot break that down into something more simple and more stable. Molecules, on the other hand, are not to be just one atom, but instead, molecules are going to be two or more atoms that are bonded. Now notice how it doesn't have to be the same atom. That's a misconception that I think people get from this. Molecules just are any atoms. So I'm going to write here any atoms. It doesn't have to be the same. They just have to be any atoms on the periodic table. And that could be an element bonded to itself, or it could be two different elements that are bonded. Can I break down molecules? The answer is sometimes. And you're going to see here when we go through these examples why the answer is in fact sometimes. And then there's compounds. So molecules are two or more atoms that are bonded. All we really need to do is just add a whole other word in there. Compounds have to be two or more different atoms that are bonded. So again, just because compounds are different doesn't mean that molecules are the same atom. Compounds must be different, whereas molecules can be different or they can be the same. Compounds can always be broken down. So yes, they can. Let's do some examples with these that are listed up here. So the first one is ammonia, NH3. So ammonia is comprised of nitrogen atoms and hydrogen atoms. And you could tell that just by looking at the formula here. So what type of matter would ammonia fit into best? Well, it probably fits into a compound. And that's because you can take ammonia and you could break it down into its elements. Not only is it two or more different atoms that are bonded, but it's also two or more atoms that are bonded. So really, ammonia is both a molecule and it's a compound. And that's why we say sometimes, because in this case you can break it down. Ammonia, just like we did with the electrolysis of water, can be broken down into its elements. So I can break this down into nitrogen and hydrogen. The next one is helium gas. So notice here, it's just that one element, and that's it. Helium is not bonded to anything else. Because helium's not bonded to anything else, it's not two or more atoms bonded, this must be the smallest unit of matter. Helium gas, therefore, must be an atom. It's just one thing. I can't break that down into something more simple and more stable. The next one is phosphorus. Now notice phosphorus comes in groups of 4. It doesn't like to exist on its own. So I literally have 4 phosphorus atoms that are bonded to one another. Because I have 4 phosphorus atoms that are bonded to one another, again, they're bonded. So in this case, this must be a molecule. It's 2 or more atoms that are bonded. In this case, I have 4 phosphorus atoms put together. So here's the difference between the two, which is why the answer to this is sometimes. So ammonia, like I said, we can break down into its elements. So I'm just going to move this down here. I can break ammonia down into nitrogen and hydrogen. I'm going to put 2's there because technically that's the correct structure for that, or the correct formulas. Phosphorus, however, I can't break phosphorus down into anything more simple and more stable. It's already just phosphorus. It's one type of atom. Can't break that down anymore. Phosphorus, therefore, is not a compound. It's just a molecule. We can cross off phosphorus here. Let's look at krypton. So krypton is just one type of element on the periodic table, not bonded to anything else. Therefore, krypton must be an atom, and there's just one atom that makes that up. Water. Water is comprised of hydrogen atoms bonded to oxygen atoms. Therefore, water is a compound. Is water also a molecule? Yes, it is. And that's because it's got 2 atoms that are bonded. Whatever is a compound is also a molecule, but not all molecules are compounds. And you saw this with the electrolysis of water. You could split compounds apart. So can it be broken down? Yes, it can. All compounds can be broken down into something more simple and more stable. And usually that's through electrolysis. So I'll say yes, usually through electrolysis or heat. Next one is oxygen, which is O2. So it's just one element, but I have two oxygens bonded together. So in this case, this must be a molecule because it's two atoms that are bonded. Not a compound, because it's not different atoms, different types of atoms, I should say, but they are bonded. Same thing with this one, Cl2. So chlorine bonded to itself as a molecule. Can't break that down into something more simple and more stable. It's already just chlorine. Sulfuric acid, H2SO4. This is going to be a compound because it's made up of hydrogen atoms, sulfur atoms bonded to oxygen atoms. And you can break this down. This actually breaks down into water and sulfur trioxide. Is this a molecule? Sure it is, because it's two or more atoms that are bonded. So literally everything that's a compound is also a molecule, which is why I added that arrow right there. Remember that all compounds are molecules too. Two more. Gold. It's just one atom. That's it. So in this case, this must be an atom. And salt. Sodium bonded to chlorine. In this case, this must be a compound. And whatever is a compound is always a molecule. And you could break salt down into its elements using electrolysis. All of these you can. Actually, you can always break those down. These ones you can't. Phosphorus I can't break down into anything else more simple and more stable. Same thing for oxygen and chlorine. So that was sample problem 1. Let's go ahead and continue with types of mixtures. So of course we have the periodic table of the elements. If you were to have just any one sample of any element, that would be a pure substance element, or a pure substance element made up of single types of atoms. So like I said to you, element number 83, this is bismuth. This is just the element bismuth. This is a pure substance element made up of atoms. If you were to have a copper penny, that would be a pure substance element made up of just that atom copper. And there's a lot of different elements you can find just kind of on their own, but I don't want to talk about that in this video. These elements come together. Oh, there's my bismuth crystal. There it is. So these elements join together and they form compounds. And of course, a very common compound is water. So you take hydrogen atoms and you bond those to oxygen atoms. They join together via a chemical bond, and you can produce tons of different compounds or molecules. And in this case, we form water. This would be an example of a pure substance compound. Of course, if this water is not contaminated by anything else. If this is pure distilled water, like what we would find in the lab, where I take all of the impurities and the minerals out, that's a pure substance. It's just water molecules. However, once that sample becomes contaminated by something else, then it's not a pure substance anymore. A lot of times you can tell you can separate the components of a compound by doing something known as electrolysis, which is really cool. So if you were to take any sort of compound, in this case water is very simple to use as an example. So you can separate water molecules or you could separate the atoms in water molecules by running an electric current through that. And when you do that, you would separate the hydrogen from the oxygen. That's how you know if something is a compound. If you can separate those elements from one another, then you know it's a compound. If I have a sample of something and I cannot separate them, no matter what I do, that's going to be a pure substance element. Which brings us to mixtures. Now, most things in life are going to be mixtures. So mixtures are a blend of two or more types of matter. It's made up of more than one type of thing. And you can technically separate those things from one another relatively easily. So it's a blend of two or more substances that are not chemically combined, each of which retains its own identity and its own properties. And we can technically separate them if you wanted to. It's going to be really tedious to do that, but you can in fact separate them. There's two types, homogeneous and heterogeneous. A homogeneous mixture is uniform in composition, and they're also called solutions. So they're made up of a lot of different things, but it looks like just one thing. So I have this wood cleaner sitting here, and if I look at the ingredients list, this has water, caprylyl decyl glucoside, propane diol. It's got lots of different stuff in it. It's made up of a lot of different things, but it looks just like one brown liquid. That's what we call homogeneous. It's got a lot of stuff in it, but it looks like one thing. It's uniform in composition. We also call these solutions. So another example is black coffee, but if you add sugar to that, or black coffee in general, it's not just coffee. It's not a coffee compound. It's water. It has flavor compounds. It has aroma compounds. It's got caffeine in it. It's made up of a lot of different things, which you can technically separate if you really wanted to. Another example that I found is chicken broth. So I literally went through my cabinets to find some things. So chicken broth, it's made of chicken broth, salt, dextrose, natural flavoring, onion powder, blah, 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 blah. It's made up of a lot of different things. However, if you were to pour this out, it does look like just one yellow liquid, homogeneous mixture. As opposed to a heterogeneous mixture, I think these are the easiest to identify. These are not uniform in composition. So something that would be not uniform, I just had this in my house. I have a little jar of old keys just because I think they're kind of fun to look at. And I have them in this old peanut butter container. So all of these are different from one another. So if I just take some of these keys out to show you, it's a jar of keys, but here's a string. But they're all a little bit different. So not uniform in composition. You could pick apart the different components of this. So because you can literally see the different parts of this, this would be called a heterogeneous mixture. A salad would also be considered heterogeneous. You can pick apart the tomatoes and the onions and the green peppers from the lettuce and all of that. So it's not uniform throughout. Just like how this jar of keys is not uniform throughout. Just like how I have this bowl of Post-it notes and things. So this is heterogeneous because you can pick apart the different components of this. Let's do some examples. So Kool-Aid would be an example of a homogeneous mixture. You can technically separate the sugar solution from the water, and you can do that, of course, by evaporating the water. You can separate homogeneous mixtures by physical processes, so by filtering or by evaporation. This would be considered heterogeneous if you consider the ice cubes on top. So you can pick apart those ice cubes with your hands and pick them out, and that would be considered heterogeneous. Chicken noodle soup, of course, is heterogeneous. You could see the carrots from the broth, from the noodles, from the chicken. You can easily distinguish all of those from one another. It's not uniform in composition. Honey is a homogeneous mixture. It is not uniform, or it is, uniform in composition. Made up of water, lots of different types of sugars, more than one type of thing. Definitely homogeneous mixture. Any type of cereal, so you could separate not only the cereal particles from the milk, but you can also separate the different colors from one another. Heterogeneous mixture. Soda's interesting, and that's because when you crack open a soda, of course it has carbonation in there, and that carbonation makes soda a heterogeneous mixture. You have the gas in a different state of matter from the rest of the sugary liquid, and they can be separated. You could have soda in a homogeneous mixture if, of course, you were to let the soda go flat, which does not taste very good. So, but that's how you can differentiate between heterogeneous and homogeneous. Homogeneous, like I said, you can separate them using physical processes. It would be very annoying to do that. Don't get me wrong, but you can technically do that. Heterogeneous, you could separate with your hands, or in this case, you would just let the carbon dioxide bubbles escape from the top. We're going to do a nice little classification lab with these in class. We'll do a little electrolysis demonstration, so that'll be pretty cool for you to see how we can split apart compounds. And of course, let me know if you have any questions, and I will see you in the next video. Bye.